Hello everyone, I am Shoeb Mohammad from MOBIS India Research Institute, SQAgroup. Today's presentation is about performing large-scale software tests at MOBIS. Today we are going to cover two sessions about software unit testing. Second session, software unit testing in MOBIS. About software unit testing, we will cover software unit testing and environment, test case design method, software unit testing in SPICE, software bug detected in software unit testing, real world status and challenge points. Software unit testing and environment. We have two topics. First is software unit testing. Unit testing focuses on the testing component in isolation. It requires specific support such as test harness or unit test framework. Software unit testing environment. In this, we are having three sections: test case, test harness and software unit. Software unit is your target function which has to be tested. Test case is an execution procedure of a unit in which we provide the input values and expected output values from design spec or code. Test harness consists of test driver and test stub. Test driver is nothing a calling test module with a design test input data and checking the actual output and expected output. Test case design method. There are two types of methods: black box testing, also known as specification based testing. Test cases are designed from specification documents. Techniques which are used in this are equivalent class partitioning, boundary value analysis, design table, pairwise combination. Second technique is white box testing, which is also known as structure based testing. Test cases are derived from the software internal structure, example code, control flow, architecture. It will cover your statement, brand coverage and MCDC. In this example, for a software unit function A to be tested, we can test with specification based test cases or coverage based test cases. Software unit testing in SPICE. Software unit verification in software engineering group is SWE.4. It provides the implementation software unit for testing and meeting the requirement. It covers static analysis, code review, unit testing, which includes your regression test. We ensure the bidirectional traceability is achieved between unit specification, test case specification and test result. And for the code review, the test results traceability is achieved. Software bug detected in software unit testing. Software bug related in unit specification. Whenever we execute a test case and there is a mismatch between the expected output behavior and the actual output, the bug is identified and depends upon the design and the test spec been written. There are different types of bugs detected in unit testing. Usually it is array overflow, divide by zero or mistake by design logic. Real world status and challenge points. Software complexity for mass production in MOBIS. based on the MOBIS reference to test 198 projects for different products and variants. The slot is around 4.2 millions, which need to be performed unit testing. To test this, we may need 158 engineers to work for 9 months based on 150 slot per day test as a productivity. The major challenge here in unit testing is about the manpower, the investment cost, the budget, and the more important thing is your test quality. Now in this session, we are going to understand software unit testing in MOBIS. During this session, we will explore the following topics: manual software unit testing, software unit testing with commercial tool, MOBIS software unit testing strategy, automate more and more software unit testing with MIST, lessons learned and future work. Before we start this session, let us take a moment to walk through the unit test framework and its components. In software unit testing, we have seen various components required, such as test cases, test driver, test stub, and test data. Now, let us try to understand how MOBIS moved from a manual software unit test to an automated unit testing. Manual software unit testing involves engineer manually developing all the test related components including test cases, test driver, test stub, and test data. Various unit testing frameworks are available for different programming languages including Google Test, CPP, UTest, CUnit, and JUnit. Here is an example using Google Test. To test the target function name as equal underscore divide, which returns an integer value. In the Google test environment, manually you will be creating multiple test cases with different input test data like 4 and -3 and use an session macros to validate the results against the expected values such as 2 and 1.5. Developers find it straightforward to implement unit test framework and test individual units. In contrast, many software unit testing is a time-consuming approach that demands additional effort for test case development and execution. Now, let us explore unit testing with use of commercial software tool. Many industries now utilize commercial software tools for C language code-based unit testing, such as Vectorcast, LDRA, and SureSoft CodeScroll. Using commercial software tools offers several advantages over manual software unit testing. Test harness creation. Commercial tool automate the creation of the test cases including test driver and test stub. Test input generation. Commercial tool automatically generates test inputs based on the data types, eliminating the need for a manual input creation in manual unit testing. Test result and coverage. Commercial tool simplify the verification of test result and code coverage compared to manual process of checking the coverage and test result. Productivity. Based on MOBIS executed project experience, commercial tool has increased the productivity, achieving 250 slots per day compared to the manual productivity of 150 slots per day. While the productivity has increased, it's worth noting that more effort is required for test analysis and addressing large scale source code testing. Software unit testing in MOBIS. Let us now see how MOBIS applies its test strategy to address large-scale source code testing. Based on our analysis, we have observed that 60% of the effort is dedicated to the test case preparation, which includes test data generation, followed by an additional 20% of effort spent on analyzing the test results. Upon closer examination, we have noticed that although most of the test data generated by the commercial tools is based on data types, it often results in feasible data, leading to extend test case execution time to increase the code coverage. In response to this challenge, MOBIS conducted research to find a solution and identified concurrent testing technique as a viable approach. As a result, MOBIS has developed its own software unit test tool named MOBIS AI Software Testing. Since 2019 onwards, MOBIS has been utilizing MIST to efficiently manage and execute large-scale source code unit tests. Now, let us explore how the concurrent testing technique is applied within the MIST to address these testing challenges. To automate more and more software unit testing with MIST, let us understand what is concurrent testing technique and SMT solver. Concurrent testing, also known as dynamic symbolic execution, known as CROWN in MIST. CROWN generates test input data for a specific source code target. To ensure the creation of feasible test data, we utilized SMT solver Z3 in conjunction with the concurrent testing technique. Let us understand the concept with an example in which we aim to achieve 100% statement and 100% branch coverage. Consider the target function name as sample having 3 input parameters, and our objective is to test the logic located at position number 4. To accomplish this, we need to satisfy 3 nested if conditions. The concurrent testing identifies the number of symbolic paths present, also known as branches. Simultaneously, the SMT solver determines the minimum test input data set required to satisfy all the branches and the statement. In our example, employing 4 sets of value enable us to cover all branches and fulfill the requirement of the target logic. Now, let us understand how MIST software tool works. The MIST tool has been developed for testing C language source code. Within the automotive industry, where a significant amount of data is transmitted via the CAN protocol using bit fill and function pointers, there are certain limitations exist when applying the concurrent testing. These limitations pertains to the handling of bit fill data and the management of function pointers within the SMT solver. However, MIST offers a solution to address these limitations through its support for symbolic bit fill handle function pointer for SMT solver. MIST comprises of 3 essential components: test harness generator, which includes the test driver and the test stub, MIST converter and MIST test input generator. Initially, the MIST harness generator analyzes the input C source file and generates test driver and stub functions of each function task present in source file automatically. Subsequently, MIST converter comes into play by replacing the bit fields with the data array of byte. Additionally, it substitutes all arithmetic expressions related to bit field with equivalent expression that operates on data array using bitwise operator. Following the generation of test inputs, MICE tool uses Crown, which utilizes various symbolic search strategies to enhance test coverage. To further increase the test coverage and reduce the test execution time, MICE is having 4 search strategies: DFS, reverse DFS, random negation, and control flow graph. This search engine approach ensures that coverage can be continuously monitored and verified for the target C file and function. For more information about the MICE, please refer the research paper published in ICSE 2019. Now, let us see MICE capability of detecting different types of software bug. MICE is having a capability to detect 3 types of software defects, namely null pointer error, array out of bound error, divide by zero error. Moreover, MICE has intelligent functionality for automatically inserting assert code where there is a potential of code failure. This feature allows it to closely monitor the assert failures and capture the test evidences including input values, location, and test failure information. For instance, in case of null pointer scenario, MICE automatically inserts assert code just before accessing a structure pointer variable named as S. When getNode function returns a value as a null, the assert result will register as a failed, and the test log will capture the details in test case failure. Similarly, in scenario involving array out of bound, MICE automatically insert assert code before accessing an array index named as A. If the value of the array index A exceeds the bound of the array, example surpassing a range of 5, the assert result will register as a failed, and the test log will comprehensively capture the details of the test case failure. Furthermore, for cases involving divide by zero scenarios, MICE inserts assert code just before division arithmetic operation take place. If the variable b holds a value of 0, the assert result will be failed, and the test log will be record essential information regarding the test case failure. This assert injection approach is a valuable resource for engineers, enabling them to proactively identify the potential points of software failure and pinpoint the corresponding input values that trigger such failures. Till now, we have seen the MICE functionality, MICE bug detection techniques. Now we will see MICE achievement and future work. Summarizing the MICE capabilities, we have observed a significant enhancement in productivity when utilizing this software tool for C language source code. Specifically, we have achieved a productivity rate of 800 slogs per day, which represents a substantial improvement compared to the manual unit testing and using commercial tool. To provide a concrete comparison, to test 4.2 million lines of code, we would require 150 test engineers for manual software unit testing. However, with the adoption of MICE as our software testing tool, we would require only 30 test engineers to accomplish the same testing objectives. Now, let us shift our focus to the future plan for the MICE. First, we aim to integrate CI/CD, that is continuous integration and continuous testing setup with MICE, enabling us to effectively respond to the continuous regression unit testing and contribution to the enhancement of software quality. Second, We are actively working towards achieving the compliance with the A-SPICE regression test strategy, thereby ensuring our alignment with industry standards and best practices. These future initiatives will further strengthen MICE capabilities and its role in optimizing the software development process. Thank you.